Let's take a look at London dispersion forces. London dispersion forces are the intermolecular attraction between temporary dipoles caused by small movements of electrons within atoms or molecules. They are the weakest of the intermolecular forces, and they are found in all atoms and molecules because all atoms and molecules have electrons. Let's take a look at an example. Here we have a molecule of dibromine. On the top row, we see the electron distribution. That single covalent bond has 2 electrons in it. If we assume that the 2 electrons are evenly distributed between the 2 bromine atoms, then the corresponding charge map will be entirely neutral. On charge maps, green means neutral, red means negatively charged, and blue means positively charged. Since the electrons are evenly distributed and the charge map is completely neutral, the corresponding dipole moment is non-existent. There's no dipole because there's no separation of charges. Imagine, however, that the electrons in that single bond decide that they all want to slosh towards the right-hand bromine. Now we have a separation of charges. There's more electron density on the right-hand side of that bond than there is on the left-hand side. That's going to lead to a change in our charge map. You can see that it's still green in the very middle, but over on the right-hand side, where all the electrons moved to, now we have a slight negative charge. Whereas on the left-hand side, that's been abandoned by the electrons, we have a slight positive charge. You may remember the delta plus and delta minus notation from when we were learning about dipoles last semester. Now, because we have this little separation of charges, we have a corresponding induced dipole moment, and it points from the left to the right, from the positive end to the negative end. But what would happen if the electrons decided to slosh the other way? If they did, they all crowded towards the left-hand bromine instead, then our charge map would flip around. Now we have the slightly negative end on the left and the slightly positive end on the right, and our dipole moment has flipped. Let's take a look at this on a more practical level. Imagine we have a couple molecules. At 10 milliseconds, each of these has a slight induced dipole moment because they've got electrons sloshing. The 2 molecules to the right are interacting with each other because their positive and negative ends are next to each other. There's a little interaction there, but some time passes. At 20 milliseconds, the dipole of the middle molecule has flipped. Its negative and positive ends have switched places. Now that we have these 2 negative ends next to each other in the right-hand molecules, there's no longer an attraction. There is instead a repulsion. If we wait a few milliseconds more, this positive side of the middle molecule will notice, oh hey, there's a negative site on the molecule to my left. I'm going to go and interact with that because opposite charges attract each other. This type of dipole flipping and electron sloshing is going on all the time. So you've got this constantly changing network of small temporary interactions. Factors that lead to stronger London dispersion forces include having heavier molecules and atoms because there's more electrons to slosh around, making bigger dipoles, or having longer molecules. A longer molecule allows greater distance to separate those charges, and greater charge separation leads to stronger dipoles. The stronger the dipole, the stronger the London dispersion force. See you guys Friday.